Okay, now in the last video we looked at differentiating functions of the type sine of fx or cos of fx, but every time I took this fx function to be some polynomial, so it was always something like, say, sine of 2x squared plus 5x or cos of some other polynomial. But of course this function here does not have to be a polynomial. It could be any function like an ln function or e to the power x function or another trigonometric function itself. So in this video I'm going to take similar examples, but I want to change this function to something like e to the power x and ln x and functions like that. So the first one, let's take a relatively easy one. Let's say y equals sine of e to the power x. What's the derivative of sine of e to the power x? Now the first thing to notice is that this is quite different from sine x times e to the power x. So if I have y equals sine x e to the power x, this is a product rule. This is a case where you'd want to use the product rule to differentiate, because the sine x is one function, e to the power x is another function. Whereas this one is a composite function where I have e to the power x, where I have the sine of e to the power x. So this is an instance where you want to use the chain rule. And in this case, I will always use the shorter form of doing it. I'm not going to use the detailed method. But if you want to use a t substitution, then your t is equal to e to the power x. But what we said was, when we have sine or cos of some function, always first differentiate the sine. So the derivative of sine x is cos x. But in this case, instead of cos x, I'm going to get cos of whatever this function is, cos of e to the power x. And then we said we had to differentiate this, multiply it by the derivative of this inside part, or the derivative of this function. So I would get cos of e to the power x times e to the power x. Or I could rewrite that as e to the power x cos of e to the power x. Okay, let's take another example. So that was a relatively easy one. So let's say we have y equals, say we'll use something with ln. So let's say we have the sec of ln x. So let's say we have y equals sec of ln x. And once again, this is a composite function. I have the sec of the ln of x. Now to differentiate sec x, you can check from your formula booklet, or if you remember it, the derivative of sec x is sec x tan x. So I'm going to get sec of some function. I'll just leave that as a blank. So sec x tan x. But instead of x, I got this function here. I got ln x. So I'm going to put sec of ln x tan of ln x. And this is dy over dx, by the way. And then I got to multiply all of this by the derivative of this part. Now the derivative of ln x is 1 over x. So I could rewrite that as divided by x. So I get sec ln x tan ln x divided by x. Okay, and once again, in this case, if you want to use a t substitution, you can use t equals ln x and then proceed using the longer method or the detailed method for solving this. Okay, let's take another one. And this time, let's say we have y equals, okay, I'll take one with the cosec x function. So let's say we have y equals cosec of e to the power 3x plus 5. Okay, now dy over dx will be equal to, now the derivative of cosec x, if you check your formula booklet, will be minus cosec x cot x. So this is going to be minus cosec x cot x, but instead of my angle is not x, it is e to the power 3x plus 5. It's going to be e to the power 3x plus 5, e to the power 3x plus 5. And then I got to multiply this function by the derivative of this part. Now the derivative of e to the power 3x plus 5, so I'll write that on the next line here. So I got to multiply all that by e to the power 3x plus 5. And from our video on differentiating e to the power x functions, we know that I take the derivative of e to the power x is e to the power x, but then I got to multiply it by the derivative of this power. So that is equal to 3. So in this case, my derivative will be, if I want to write it separately, I could say minus 3 e to the power 3x plus 5 times cosec e to the power 3x plus 5 times the cot of e to the power 3x plus 5. I know these are harder examples, but if you can do this, then I think the ones in the exam will be very, very easy. Okay, and remember, the composite functions can also be multiple trigonometric functions. So let's take something like this. Let's say we have y equals the sine of cos of x. So this is the sine of cos. This is not sine x times cos x. This is the sine of cos x. So dy over dx once again will be equal to, and if you want to use the chain rule, your substitution should be t equals cos x. So I'm going to do it in one step. So the derivative of sine x is cos x. So I'm going to get the cos of whatever that function is, in this case, which is equal to cos x in itself. Then I got to multiply by the derivative of the inside part. The derivative of cos x we know is minus sine x. Minus sine x. So I can rewrite this, bring the minus to the front, and I'll write this as minus sine x times cos of cos x. Okay, and then let's take one last example, and of course you can also get the product rule with this composite functions as well. So let's take something like y equals the cot, and this is going to be a much harder example because I'm also going to use the product rule in here. So I'm going to have, let's say I have y equals cot of x e to the power, let's say 3x squared. And I think if you can do this in one step, then I think you really understood the chain rule and how to differentiate trigonometric functions. Now the first thing to check is what's the derivative of cot x. The derivative of cot x is minus cosec squared x. So I'm going to get minus cosec squared of this function. So that turns out to be x e to the power 3x squared. But then I got to multiply it by the derivative of this part. Now remember, now this x e to the power 3x squared is a product. So I got to use the product rule on that. So I got all that times, I have u dv over dx plus v du over dx. So if I take the u dv over dx part first, I have the first function x times the derivative of e to the power 3x squared. Now the derivative of e to the power 3x squared is e to the power 3x squared times the derivative of this top part here, times the derivative of 3x squared, which is 6x. So remember, now this was u times dv over dx. This part here is the derivative of e to the power 3x squared. Then I got plus v times du over dx, the second function, times the derivative of the first. Derivative of x is 1, so this works out quite easily to e to the power 3x squared. Okay, and if I simplify this, I would get, now this here can be written as 6x squared. So I'll rewrite this as minus cosec squared of x e to the power 3x squared times 6x squared e to the power 3x squared plus e to the power 3x squared.